let's talk about the first derivative test. This is very important. To find maximum and minimum values of a function. Notice that sometimes we are actually concerned with when's the function the greatest, and if you want to think about it in terms of money, when is the profit the greatest, or when's the best time to, sell? When is it? When's the function going to be its maximum value? And also, when is it going to be its lowest value? Or when should we not, or when should we buy? In other words, if you're thinking about stocks. If a stock or something is looking like this, very up and down, we probably want to know what the maximum value and what the minimum value is. And the way you can actually do that is if we model the change in terms of a function f of x, we can find maximum values and minimum values, local max and local min, if you remember from a previous video of mine. And we want to talk about how to do this with the first derivative test. We can find derivatives very easily, and what can they be used for? This is one application, the first derivative test. So let's talk about it. There are several parts to this. One dealing with interior points. And let's talk about that one first, and the other one being exterior or boundary or endpoints. So, interior points. We want to find critical points, or let me write it, critical point. Recall that this is when the derivative of the function is equal to 0, or finding x values where it's equal to 0 or undefined. Notice that here is a critical point because it's 0, here is a critical point because it's 0. There are also cases where it's undefined, for example like this, where it's a sharp point, or where it's like a cusp, this type of thing, undefined. And we want to actually just note these because we can't actually find the derivative, so we call them critical points because we should still look at them just in case, because notice that this is a type of local max and this is a type of local min. But we can't find a derivative at that point, so that's why we want to keep undefined points in mind, and which is why they're critical. So interior points are very special. Given that the point we found to be critical, I'm going to say a point x equals c is critical, or a CP. I'm going to draw a couple graphs, and we're going to talk about them. So I'm going to draw this graph, and this graph. Very weird. And we know that this is a critical point, this is the critical point, and this is the critical point, because the slope is 0 here. What does the first derivative tell us about a function, right? First derivative tells us about slope. What is the slope of the function at a specific point? Thinking about it as rates of change, is it going to increase or decrease? That's the other idea of first derivative. Increases or decreases, we can actually represent them in terms of a sign, positive or negative. So notice that at this point, at this critical point, everything to the right of it is a positive type of derivative, right? The slope or the tangent lines at every point here is positive. Similarly, on the left-hand side, everything is negative. So taking tangent lines, they're all negative slopes. See? Very, it makes sense, right? If we change from negative to positive, we have a local minimum. And that's always true. We have some type of local minimum because it changes from negative to positive at that critical point. And you can see it through this picture that it makes sense. And then same with this one. This is a positive, 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 positive. At the critical point, it switches to negative, negative, negative. And this is the critical point. And then the same thing. If I draw tangent lines here, right? Notice that it's positive on the left-hand side, but negative on the right-hand side. If this is true, it's a local max. So here, let me just show you It changes from negative to positive, or the first derivative, and then this one is positive to negative. And then we have this third case where it's not going to change sign. It's going to be positive and positive. Positive, 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 positive until the critical point, and then positive, positive, positive. Same thing with this type of thing. It's going to be negative, 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 right? Negative at the point C. We give this name neither. A more technical name would be a saddle point, a saddle. And the reasons why it's called a saddle is actually saved for when you look at it in higher dimensions. When you want to actually maximize and minimize functions at higher dimensions, we actually see saddle points, or saddles, things that resemble saddles. But these don't really represent saddles because these are a two-dimensional case. So we go positive to positive or negative to negative, right? Notice these signs. We're only looking at signs, not too much of values. And that's going to be key with the first derivative test. This is the first part of the first derivative test. Let's talk about the second one, which is about endpoints. Endpoints are very tricky to work with, especially with functions, because a lot of people end up not understanding too much about endpoints. We want to look at the left endpoint, or the A part. The A. So let's say this is A, and here's another one, another A, the left hand, right? So it's going to continue on the right hand side, but here we're only looking at the left endpoint, or the starting point. Notice that since this value, every value to the right of A is going to be greater than this point. This is a minimum value, a local minimum. And the way we, I guess, formalize it is that if the derivative is always going to be positive for values of x that are greater than a. In other words, values that are greater than a following this arrow, right? Bigger than a, it's positive, right? Positive, positive, positive. Let me write it in green to be consistent with the previous drawings. It's positive, and for all values that are greater than a, that means a must be a local minimum because there's nothing that goes smaller than it, because this is true. And then similarly, for values that are greater than a, or x values that are greater than a, if these are minus, minus, minus for all the way through, this is called a local max. So this is a local max and this is a local min. And the way we formalize this very similarly is that if the sign of the derivative, first derivative is 0, in other words negative, for values that are greater than a. And then we want to look at the second part of the endpoints, the b, right? The b, so this is the a. Let's talk about the other part, b. Very similar. Let's say I have something that looks like this and something that looks like this. And this is the b part, b, and this is b. Very similar. Notice that these are all negative, and then these are all positive, 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 all the way until there. So if this is going to be negative, for values of x that are less than b, in other words, less than b is this way, this is going to be a local minimum right here. And then this means this is a local max because of the derivative is positive for all values that are less than b, in other words, going the other direction, leftwards. This is how we can find local mins and local maxes of endpoints. And then right above, this is how you find local mins and local maxes of interior points. So see how interior points depend on the sign changes, but the endpoints depend on the sign all the way up to the point. It doesn't matter on the other side, right? Can't change because this is where it stops. So we just have to look at the behavior to one side of it. I wouldn't get too caught up with this notation here. Just get a good picture of the endpoint one, but the interior point, you should have these kinds of pictures drawn in your mind, and then you can automatically get from the picture to a statement. Minus to plus, right? Minus to plus, plus to minus, And then plus to plus, minus to minus is neither, but this one's kind of hard to imagine. You just have to visualize more of the pictures and it makes sense in your head. More than these symbols, because I know these symbols look very confusing at the bottom. So endpoints look more of the pictures, and interior points also look more at the pictures, but with interior points you actually also want to look at the sign, because that's going to determine if it's a minimum or a maximum. And the interior points are very important for especially the next couple examples we are going to do in next videos or in future videos. So this is the first derivative test. Notice that's very helpful to find max and minimum values of functions, and imagine it modeling something in real life. You want to know the max and min, and the way to do that, one way to do that at least, is the first derivative test. And this is what the first derivative test says. So that's it for this video.